We're going to cover some information on second order systems. Second order systems, you show right here a couple different second order systems. This one is, for example, underdamped, and you see some oscillations. This one is going to be critically damped. And then the last one is overdamped. Okay, so we're going to characterize these systems. We're going to understand how to develop equations that describe them, and a little bit of information on their derivation and use. Okay, so the standard form for second order equations this is going to be in the Laplace domain, where we have a gain, a natural period of oscillation, tau, and then we're also going to have the damping factor, which is zeta. Okay, and then as we go on, we have just one note about this, is that this number has to be 1. So if it's not 1, then you have to divide both top and bottom by that number to make it 1. Okay, so the critical thing there is that needs to be 1 for a standard form. And then the corresponding differential equation for this is shown here. If we just have 0 initial conditions, that's where we get the Laplace transform, 2 times zeta tau s times y of s plus y of s equals k u of s. Okay, and then if I just factor out the y, and then y of s, and then just have these interior terms, and I come up with this transfer function equation right here. Okay, so that's how we go from the time domain to the Laplace domain. Okay, and then we're going to work to, we can also derive this by multiple capacity systems in series, multiple first order systems in series. Okay, so if I have something like this, you'll recognize these as first order systems. If I have 2 of those in series, like let's say it goes into one process, let's say a tank, and then another process, another tank. So this would be like system number 1, system number 2. Okay, and if it goes, if we want to relate the inlet flow here to the outlet flow here, it's going to become a second order system because we have 2 first order processes in series. Okay, so this becomes, if I multiply these 2 together, I get that this is going to be the gain is K1 times K2, and then it's going to get into a standard form where I'm just going to multiply this out and then fit it into that form there. Okay, so if I multiply this out, I get tau 1, tau 2, s squared, plus, okay, and then this is going to be tau 1 plus tau 2, s plus 1. Okay, and then tau 1 times tau 2 equals tau squared, and then 2 zeta tau equals tau 1 plus tau 2. Okay, so that's how this standard form for second order systems relates to 2 first order systems. Okay, so let's look at the characteristic equation. This is the denominator. Okay, if we had k on the top, this is the characteristic equation. We call it that because we can tell about the stability, the the behavior just by looking at the roots of the denominator. And so we're going to just analyze this. We're going to set it equal to 0, and then look at the roots of this characteristic equation. So if we get into this form and we look at the value of zeta, if it's greater than 1, then it's going to be overdamped. If it's equal to 1, it's going to be critically damped, and it's between 0 and 1, it's going to be underdamped. And where this comes from is really, you can look at the quadratic equation. S equals negative 2 zeta tau, that's negative b plus or minus square root of b squared. So that's going to be 4 times zeta squared, tau squared, minus 4 times a, which is tau squared, times c, which is 1. Okay, and then over 2 times a, which is tau squared. Okay, so if this value right here inside the square root is, if that is going to create an imaginary number, then we know it's going to have these two complex conjugate roots, and it's going to oscillate. Okay, so it's going to come up and it's going to oscillate, okay, because it has imaginary roots. But if this is going to be positive, then and then what we'll see is going to be not have the oscillation and just converge to the new value. It's critically damped, or just a little bit slower, it'll be underdamped. Okay, so that's where that comes from, these rules right here in terms of the zeta value. Just remember, if it's between 0 and 1, it's going to be underdamped, and there's going to be some oscillations there. Okay, so responsive second order system to step inputs. Just a couple equations here. We have underdamped. In the book that you have, you'll just use these equations to describe them. But there are the equations that characterize these different responses. And for underdamped, only for underdamped, where we have a little bit of overshoot and oscillation, we're going to have things like rise time, settling time, decay ratio, time to the first peak, overshoot, and period of oscillation. That helps us be able to model the second order response with and be able to determine the constants. Okay, so let's just look at rise time first of all. That's going to be the time the process takes to first reach the new set point, okay, or the new steady state value. So here we have the rise time right there. Here, this is the steady state value. As I draw that along, the time to the first peak is TP. The settling time, it's when it reaches within 5%. Okay, the first time that it gets inside that dead band and stays there is right here. So that's going to be our settling time. And then our overshoot is going to be this A divided by B. Okay, and then the decay ratio is going to be C divided by A right there. Okay, and then the period of oscillation is the time between two peaks on one side. Okay, so it's not this one down here, and it can also be the time to this peak. So that is another period of oscillation. You could also do it between two peaks and then just divide by 2. That'd be 2p, and that helps you remove some of the uncertainty with regards to where the peak is. Okay, so and then if we look at the equation for this, okay, here it is in the time domain. You can see a cosine and a sine. That gives us the oscillation, but then it decays out. It's multiplied by this exponential term, so you can see them getting smaller and smaller as it goes. Okay, and when it goes to time equals infinity, this is going to go to 0. Okay, so it's time goes to infinity, then the e to the minus t. Anything e to the minus t is going to go to 0, so you're just going to be left with k times m. Okay, and that's going to be the final y infinity equals k times m. That's going to be the steady state value. Okay, let's go on. So as we have a second order system response to just a step input, I'm going to show you a couple here with different zeta values. You can see zeta equals 0.2, 0.4, 0.8, and then as it gets down to 1, okay, then it's going to be critically damped, so no oscillations. There's just a little bit of oscillation here, just a little bit of overshoot, but then when it gets to 1, then it's going to be critically damped and no more oscillations. Okay, and then here's the critically damped. Okay, so as we continue down on the zeta values, here's zeta equals 1, that's critically damped, and then zeta equals 3, that is overdamped. Okay, so it gradually, so that might be 4, 5, 6. Just it's going to get more and more damped and approach the new steady state value more slowly. Okay, so also one other thing to note, is zeta is less than 0. That's going to give us an unstable solution. So the oscillations will grow. Let's say we did zeta equals negative 0.1. We might have something like this where it's just going to grow out of control. Okay, let's go on to the next one. So there's relationships. This is just for underdamped systems. These equations do not apply for critically damped or overdamped. It's just the ones with the oscillations. Okay, so we have our peak time. That's how it relates to tau and zeta. Here's our transfer function. Just to remind you, we have 3 unknown parameters here: k, tau, and zeta. M is the magnitude of the step that we gave it, and then this is going to be the response. Okay, so we have a step of m, and then it's going to then settle out to k times m. But along the way, we're going to have our peak time, okay, and then overshoot as well. Here's A divided by B. Okay, so we can pick out the different zeta and tau values just by looking at the overshoot, the peak time, the damping ratio, the period, and the rise time as well. Now, I'm going to show you these equations, but look at some of these. This one depends on tau and zeta. Okay, so we have, if we know the peak time, we know the relationship between tau and zeta, but we don't know either tau or zeta. And same thing here with the period, and same thing here with the rise time. They both contain tau and zeta. But look at the damping, the decay ratio, and then also the overshoot ratio. They only depend on zeta. And so that's really nice, because if you can pick out the overshoot, let's say the overshoot is maybe 0.25 there, then we can use either of these two equations right here to then get zeta by itself and be able to solve for zeta. And then we can get tau maybe by, if we know zeta and we know the peak time, then we can get tau as well. Okay, and then this is the equation for zeta, so you don't have to rearrange it. You can get zeta from the overshoot. Now, one thing about this is it's going to be the natural log of the overshoot, and then you square that. You don't square the overshoot. Okay, let's go on to the next one. I'll show you an example of this as well. We're going to do the response of a second order system to sinusoidal input. Okay, this is, instead of a step input, we're going to have a sinusoidal kind of oscillatory input. So the output is also going to oscillate. Okay, all output has a different amplitude than the input. Okay, and then the amplitude ratio is a function of zeta and tau. And we'll be looking at this equation here from the textbook. So the output is also phase shifted from the input, and the frequency omega must be in radians per time. Okay, so just remember that 2 pi radians equals 1 cycle. Okay, and then the period is the time divided by cycle. Okay, just a couple equations just to relate omega and the period and the frequency. Okay, and the frequency is this new value, nu. The frequency is in cycles per time. Okay, so if we have an input, okay, so this is our u of s. Let's say that's going to be a u of t. I'll do u of t. And let's say that is oscillating, okay, with a certain amplitude, amplitude A. Then we can compute what the amplitude after a long times after the exponential term dies out and it's kind of reached this steady oscillation for the input and the output. We can know what the amplitude of our output is going to be by using this chart, for example. Okay, so we have an omega times tau right there, and then these are the damping coefficients right here. So if you have a damping coefficient of 1, then we know that the amplitude divided by k times, that's the gain, times the amplitude of the input is going to be less than 1. But if I have something greater than 1, then it's going to amplify the output of my second order system. Okay, so the amplitude of the output is going to be greater than the amplitude of the input if this is greater than 1. Okay, so we also have an equation here on the amplitude. That's going to be this equation 563, so this relates to the amplitude of the input times the gain of the system, and then the omega and the zeta and the tau value as well. Okay, so that's just the response of a second order system to a sinusoidal input. Okay, and that note that's a log scale there on the chart that I showed you. Okay, all right, so I'm just going to go on to the next one. Here's a roadmap for second order equations. Okay, so when we have a standard form, if we have a step response, then we need to determine if it's underdamped, critically damped, or overdamped. And these equations here, we showed this, 551, 550, or underdamped. You have two different equations that you can use. And then if it's underdamped, okay, so we're going to have oscillations, and we can use the relationship between overshoot period, rise time, zeta and tau to be able to get zeta and tau from, graphically, just from looking at a plot. Okay, the other ones we might have to just fit them like we did the first order plus dead time. Okay, if we have a sinusoidal response, we showed that as well with this equation. We can just look at the amplitude of the input and output. Okay, and then we also can use other input functions, and that's where we're going to use partial fractions. Okay, so let's just look at an example here. Okay, so I'm going to just, for this underdamped system, okay, let's see if we can determine zeta and tau for that. Okay, so what we need to do first of all is look at some of our equations that we had from before. So we have overshoot equals, and then the exponential of negative pi zeta over square root of 1 minus zeta squared. So we're going to start with that, or if it's rearranged, we have zeta equals square root of natural log of overshoot, and we're going to square that, and then pi squared plus natural log of overshoot, and then we'll square that as well. Okay, so let's go ahead and calculate our overshoot. So this is the amount that I overshot, the new steady state. Let's say that goes to about 2.9, so that's plus 0.9. And then let's look at the change here, that's plus 2. Okay, so my overshoot is going to be about 0.9 over 2, or about 0.45. Okay, so now we can calculate zeta. We're just going to use this equation right here to come up with our zeta value. Okay, so we plug all of that in, then we come up with a zeta value of, I think it's about 0.25. Okay, so you can verify the calculations on that. Okay, so zeta is 0.25, and we just want to make sure that we are between 0 and 1. Okay, so that checks out there. And then we can use our peak time calculation. So let's say we have peak time equals pi tau over square root 1 minus zeta squared. We could also use the period. Okay, it's the time between here and here. Okay, so there's the period, and that equals, let's see, that's going to be 2 pi tau over square root of 1 minus zeta squared. Okay, so just twice of what that one was. Okay, so we can use either one, and we do that calculation. We're just going to solve for tau. We already have zeta from up above, and then we can calculate the period, which is about, let's see, between here and here, that's going to be about 6 to 19 or so. So, yeah, I guess that would be about right. So that's going to be about 13. Okay. So about 13 seconds for that. And so our tau is going to be about, well, let's use 14. Tau is going to be 1.52 seconds. Okay, so about 14 seconds between those two. Okay, so then our gain, let's say we had a step input of 1, then we know that our gain for this is going to be equal to 2. So therefore our total transfer function, y of s over u of s, is going to be k over tau squared plus 2 zeta tau s plus 1. Okay, and then just plugging in these constants that we determined right there. Okay, so we are able to characterize this second order system and just do it graphically. Just come up with zeta, tau, and k values just from the plot. Okay, so let's look at another example. You have a heated tank plus controller for a second order system, and when the feed rate changes up by 0.1, okay, so it goes from 0.4 kilograms per second to 0.5 kilograms per second. The temperature of the tank changes from 100 to 102 degrees Celsius. Okay, so that's going to go up to that steady state, but it's going to take a little while to get there. Okay, so let's find the gain. First of all, the gain is going to be the delta y. Okay, that's the delta y, and then this is going to be the delta u. Okay, so we have 2 degrees Celsius divided by 0.1 kilograms per second, or about 20 degrees Celsius per kilogram per second. Okay, so there's our gain that we have for this system. Okay, so now the response is slightly oscillatory, with the first two maxima of 102.5 and 102 at 1000 and then at 3600 seconds. What's the complete transfer function? Okay, so we have it goes from 100, okay, so it's going to go up, it's going to oscillate, and then oscillate again. The first one's going to be at 1000, and I didn't really draw this to scale, but to 3600 seconds. And then from this, just like we showed from the period, we also had the overshoot. Okay, so A and B. Then from that we can get our, we already got our K value, and then we can get our zeta and our tau value as we showed before. Okay, so we already did that once. I'm not going to go through these calculations. And then from that we can also predict the rise time. So even if we didn't have that, we have our rise time equation, which is tau over square root of 1 minus zeta squared, and that's pi minus the cosine inverse times or of zeta. Okay, inverse cosine of zeta. Okay, so we can also, once we have the zeta and the tau values, we can do things like predict other things about this response, like the rise time or other quantities. Okay, so we have another example, a thermal well plus CSTR just gives a second order system. So if we have you know, this thermocouple right here, there may be some dynamics associated with that. Okay, and then also some dynamics associated with the CSTR. So that's the temperature measurement, and then also the CSTR. So we want to try to get find the tau and the zeta values for those. Okay, so actually let me go back here. So if I just multiply this out, 1 over 30s squared plus 13s plus 1, and then I have that in this form, zeta 2 zeta tau s plus 1, and so tau squared equals 30, or tau equals square root of 30. We can eliminate the negative value. We're not going to have a negative tau. And then we know that 2 zeta tau equals 13, or zeta equals 13 divided by 2 tau. And I can just plug my tau value in there to get 13 over 2 times square root of 30. Okay, so I have my tau and my zeta value for this case. Okay, so that concludes this presentation on second order systems. What we did is we covered, let me just go ahead and turn off the pen there. So what we did is we covered just a standard form, okay, like this, and then moved on to the origins of the second order equations. You can either have 2 first order equations, or you can or it can be underdamped and not have 2 first order equations. Okay, so and then we moved on to some of the characteristics just by looking at the denominator and that zeta value. Okay, if it's less than 1, then you're going to have oscillations. We looked at also some of these, like rise time, peak time, settling time, overshoot and damping ratio, and period of oscillation. We also had the relationship between the zeta and the tau values and my peak time, overshoot, damping ratio, period. So these are the equations that define those. We also looked at the sinusoidal, or second of these sinusoidal inputs to a second order system and the response, and then went over just a couple of example problems.